We're live. We're live. Yep, we're definitely live. Okay, we're going to take the extreme value theorem. Extreme value theorem, it's pretty straightforward. So if a function exists on an interval going from A to B, it will reach a maximum and a minimum somewhere in that interval, okay? And of course, you have to say all these things about it being continuous and all that kind of stuff. But that's the extreme value theorem. It reaches a maximum and a minimum. That seems right. Okay, we have different terminology for different kinds of maximums and minimums, and we're going to look at a thing called critical points, which helps us determine the maximum and the minimum. Okay, so here we go. A. So this is, is this a local maximum? Internet? Yeah, this is a local maximum. Is it a global maximum? And the answer is no, it's not. Because look, this one's higher over here. Okay, this is a local maximum. Look here. Local minimum, global minimum. It's both local and global. What about this one? This is very interesting. This is like an inflection point. Neither maximum nor minimum. Okay, so the function in this neighborhood doesn't really reach a maximum, also is not a minimum. Okay. Look, local, global, maximum or minimum, local max and local min and global and local max. Okay, so our endpoints and what these turning points represent places where potentially you can get maxima and minima. Okay, this cusp right here, another place where you can potentially get local or global maxima or minima. So notice this place right here. So this is f at x, this function, f primed at x at the boundary point. Does it exist? Does the derivative exist? No, because the limit doesn't exist. Okay, so for some reason we don't say the derivative doesn't exist, but it does not exist because we can't take the limit from the left or the right. What about right here, this turning point? What's the derivative? Does it exist? Well, yes, it sure does, but it's equal to 0. Okay, so that's another example of a thing that's called a critical point, and this could potentially be local or global minimum. Okay, right here, does the derivative exist? Yes, it does, and the derivative is equal to 0. Is this a local max or min? 9, it's neither. Okay, so just having the first derivative equal to 0 is not enough to say that you've got a local or global max or min. Right here, what's the derivative? Does it exist? Sure does. Slope is 0. Okay, that's a local maximum. All right. Right here, f primed at x, is it equal to 0? Does not exist. D any. Okay. And then right here, f primed at x, this is a boundary point, and it's another d any. Okay, does not exist. What? Hollow circle? Oh, this can be the inclusive point rather than the hollow circle. Okay, even if this is a closed interval, in other words, this is a defined point, that limit still does not exist. This one exists from the left, but not from the right. So if it's an open circle, it changes it a little bit. Okay, so the question is, what if this was an open circle? In other words, we said, the function is defined on -7 to anything less than 5. So get ready to have your mind blown. There is no maximum. So we actually have to say that it is a closed interval. We have to say equal to for our endpoints, or there is no maximum here. It was a global maximum. There isn't one. Yeah. There isn't one. What's that? Yeah, so say what a maximum would be, and I'm going to find you a number that's higher, and we can go on all day. All right. So interesting point. Okay, if that's an open circle, there's no maximum. Weird. Well, not really. It is kind of weird. Okay. So here we go. We're going to get local maxima and minima at critical points. Okay, critical points. the derivative is equal to 0. That's one example of a potential critical point. Okay. Another kind of critical point, the derivative does not exist. Okay. And so boundary points wind up falling into the same category. So if we want to find the maxima and the minima, we just have to go through this process. Okay. So find where f primed at x is equal to 0 or f primed at x does not exist. And then we have to take those x values and find out what the y values are. Okay, in other words, we have to find out what the actual height or depth of the function is for those x values. So it's kind of like a 2 or 3 step process. Okay, those tell us our global max and mins, and those are the extreme values. All right, there we go. So we're going to come up with a function. We're going to take the derivative. It's just going to be a nice tame function. And yeah, there's not going to be anything really peculiar about it, but we're going to find maxima and minima. Gonna need to fix this brush. It's leaving a mess. Okay. So here's my function, carefully chosen to make things beautiful. It does not illustrate all of those cases that we looked at before. It is a cubic function. Okay. And so it's a cubic function. The lead coefficient is negative, so it might do something like this. It might not. It might have one of those hanging points, you know, where the point of inflection winds up having a 0 slope. Okay. G. We also need to put this on a closed interval, and if we don't put it on a closed interval, we just can't do this. So x is anywhere between -7 and +5, right? No open circles on this one. Oh, so I shouldn't put arrows on. I should put closed circles on. There we go. So it's defined on a closed interval. And it is going to reach an extreme value somewhere in there. Here, 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 here. We just don't know because we don't know the y values. But we can use our good old calculus and algebra to do that. So let's take the first derivative, -3x² minus 12x plus 15. There's my derivative. Continuous everywhere. I don't have to worry about any weird cusps or goofy stuff going on. Okay. We want to know where this thing is equal to 0 because it's defined everywhere. So we've looked after that part. We want to know where this is equal to 0. What do we need to do? Yeah. Okay, so for CP, f primed at x equal to 0, let's factor it. What's the first kind of factoring we're going to do? For critical points. Okay, yeah. Let us common factor, yeah. Let us now common factor plus 4x minus 5. Oh my goodness, look it. What a surprise. This thing is factoring like nobody's business. X plus 5 and x minus 1. Here come the x values everywhere, everyone. This is true. So critical points at x equals -5 or x equals +1. So we've got critical points there. We also have critical points at x equals -7. And we have a critical point at x equals 5. Okay, so I'm saying that's a critical point, even though some people call it a boundary point, and I'm saying the derivative doesn't exist, even though people say, well, that's a boundary point, but the derivative doesn't exist. Okay, good. We need to check out all 4 of these. We need to check out the y values of all 4 of these. Oh my goodness. Am I ever sorry that I didn't calculate this before, because I'm likely going to make a mistake. Okay. We are including boundary points as critical points. Okay, because the derivative doesn't exist. So we're looking for those 2 things. Is the derivative 0 or does the derivative not exist? And we're saying boundary points, the derivative doesn't exist. Okay, we have to put in all 4 of these into our function. I like the one that's a 1, but I don't know if I like the other ones. Okay. So let's do this one. We'll find the y values. We'll figure out what the maximum and minimum is here. Okay. So f at -5 is equal to negative 5 cubed minus 6 times -5 squared plus 15 times -5 plus 42. Oh my goodness, this is really going to tax everything I've got. Okay, 125 plus, this is 25 times -6. So that's actually going to be a minus. 25 times 6, am I right? Is this 150? Minus 45 plus 42. Okay, so that's -25. That's -70 plus 42 is -28. Okay, tell me now if I got that wrong. Tell me now if I got that wrong, because I'm fully prepared to accept being wrong. So this is -25 minus 45 is -70. -70 plus 28. -28. Hooray! We've just done the double check there. Okay, good. The next one is easy. I like the next one a lot. So I'm going to put in a 1. Even I can do this. I'm going to erase that. -1, 1. I'm going to erase that. Good. 1. Okay. 1 cubed is 1. -1 minus 6 is -7 plus 15 is 8 plus 42 is 50. Okay, so far I have a minimum and I have a maximum. So these two are in the running for minimum and maximum. But we have to check our boundary points or it's just not going to be good enough. Oh, -7. That's the worst times table ever. -7, -7, -7. Look, see, I can kind of cheatily turn that into a -7. Okay. Oh. Can somebody tell me what -7 cubed is? 49 times 7 is 200. What? 343. Okay, so this is 343 minus 6 times 49. This is 6 times 49. 6 times 40 is 24, 240, 290. What? 294 minus 294. And then this is going to be a minus, and that's 70 minus 105 plus 42. Okay. This is very complicated. Well, not really. So 343 minus 294. So this is 49 minus 105 is 56 plus 42 is 98. 98. All right. So this boundary point is, are you saying I got that wrong? You just said wait, like as if I got that wrong. Yeah. Positive. Okay, let's do it a step at a time. 43, 49, right? Okay. 49 minus 105 is going to be -56. -56 plus 4. Oh, I hate being wrong so much. -56 plus 42 is -14. Oh, darn it. All right. I was really rooting for that boundary point. All right. I just can't add. That's my problem. All right. Okay. Last one. So this one's, oh yeah, this is still the minimum. This is still the maximum. Let's check out this right-hand boundary point. 5s. Oh, I wish I'd done this one back when I was like doing all that 5 stuff. Yeah, well, it's not going to be the same thing because we wind up with positives and negatives. Okay. All right. All right. -125 minus 150 is negative 275. Plus 75 is negative 200. Plus 42 is negative 158. Negative 158. Negative 158. We have a winner, folks. We have a winner. Negative 158. As long as I haven't made a mistake. And if I have, I leave it to the viewer to figure out what the mistake was. So our absolute minimum here happens when x is 5 and y is negative 158. And our absolute maximum happens here. In other words, these are the two extremes, okay? So one of them is at the left boundary point where the derivative did not exist because it's a boundary point. One of them is right in the middle at a turning point, okay? So the global minimum is right here. This one is probably a maximum, right? But I don't care, it's not the big winner. But it is an extreme value nonetheless because it's a local maximum, okay? We found the y values, yeah, which is are essentially the function values. Yep, that's it. So there you go. All you have to do, go figure out the critical points, test them all out. That's it. That's what you do. All right, yeah. I guess we could actually. Yeah, actually plug it in.